Welcome to Uncovering Chemistry's Mysteries with Mr. A. I'm Mr. A, and I'll be your guide for this instructional video. But before we get to that concept, let me ask you a question. Have you ever cooked anything before? If you have, what was your first dish? If you haven't cooked anything before, what is the dish that you really want to learn to cook? For me, the first thing that I've ever cooked was instant ramen. I was about 7 years old when I cooked my first ramen. Before that, I would intently watch my siblings prepare it. And then after I understood enough of how to prepare it, I started doing it on my own. I mean, it's not that hard, right? It's instant ramen. First, you would grab the ramen packet that included the ramen and the seasoning. Then you would grab a pot, place it on the stove, fill it with water, and turn on the stove. After that, when the water starts to boil, I would just dump the ramen and the seasoning in the packet, swirl it around to mix the seasoning and make sure that the noodle is how you want it. And that's it. Turn off the stove, transfer the noodle soup into the bowl, and you're ready to eat it. It's very, very simple, right? So after cooking ramen for a while, I got a little bit fancy. You know, like it can't just be noodles and the seasoning. So I started adding eggs and hot dogs into my ramen. So again, first I would grab the ramen packet that included the ramen and the seasoning, the eggs, and the chopped up hot dogs. Then I would grab a pot, place it on the stove, fill it with water, and turn it on. Then I would add the water. Once it starts to boil, I would just dump the ramen in there and the chopped hot dogs and the seasoning in the packet. I would swirl it around to mix the seasoning with the water, and then crack the egg and drop it into the soup to continue, and then continue to swirl and mix the egg into the soup. After that, I continue to cook the noodles until how I want it. Then I turn off the stove, transfer the noodle soup into a bowl, and then I'm ready to eat it. Again, there's this process that I followed, and very simple one to cook my instant ramen. Now that I've shared with you how I prepare my ramen, let's play this little game. If you were a chef, how would you go about making a lasagna dish? What's the first thing that you would do? What would you do after? If there are any other steps, what would it be? I'm assuming the first thing that you would do is grab all your ingredients, right? You probably would grab your lasagna sheets, the cream cheese, if you wanted to add meat into it, some onions and some other seasonings like basil, salt, ground pepper, right? You'd probably just gather all the things that you need to prepare it. The second thing that you'd probably do is follow the procedures. You'd probably have some sort of recipe or video that you would watch and follow the procedures on how to make a lasagna, right? Just follow the recipe or the instruction to the T on what to do step by step on how to cook the dish right. After cooking it, you end up with a yummy, delicious meal. There you go. Great job, chef. With that, guess what you just uncovered? You have just uncovered one of chemistry's mysteries, stoichiometry. So let's start with this. What is stoichiometry? Stoichiometry is a discipline of chemistry that involves balancing equations and determining the amount of reactants needed for a chemical reaction or the amount of products made from that chemical reaction. So it's kind of like cooking. So stoichiometry and dimensional analysis, again, just like what we did a couple of minutes ago where we prepared the lasagna, right? You needed your ingredients, you needed to follow some sort of procedure, then you end up with the finished product. So stoichiometry is exactly like cooking a dish. You prepare and gather your ingredients, kind of like in the lasagna. Here, I have an example of gathering up my ingredients like hydrogen gas and oxygen gas. Then you follow the procedures to work with your ingredients. Just like the lasagna, we followed our step-by-step procedure on how to prepare it. And then after your ingredients mix or do what it needs to do, it turns into something new and you end up with your final or your finished product. So today we will go over just that. We will go over how to do stoichiometry. We are going to be using the full stoichiometry map this time. If you do not know how to do the basic dimensional analysis process, please watch our previous video discussing and going over the basic of dimensional analysis. I would add the link on the bottom, but the video should guide you on how to convert a given unit into moles. We actually use a couple of tools from that video We use the mole map to do some dimensional analysis, doing conversions. But today we'll do a little bit more than what we did before. We'll do a little bit more of an advanced setting for stoichiometry. So let's get started. Before we can fully utilize that full stoichiometry map though, we will go over some of the basic concepts that we need to apply and use. So let's start with this concept. To do these concepts though, we need some tools to help us. For today's video, you will need three things. You will need your periodic table of the elements. We need our common polyatomic cheat sheet to help us with our chemical equations. And then we will need our full stoichiometry map that ends up with our three things that we need. So let's gather all these tools first. Please open up a new window so that you can access these tools as we go about our problem. Again, you need your periodic table of the element. I always go to ptable.com. It's just a little bit more accessible. You should have your list of common polyatomic ions to help us with balancing or writing down our skeleton equation. And then we need a full stoichiometry map just so that we can visualize where we are starting and where we want to end. And this should help you visualize the things that we need to do step by step. You can either use this stoichiometry map or a little bit more basic one, right? Whatever works for you. Please go ahead and use that. Now that you have all those tools, let's get cooking. The most important step in stoichiometry is having the correct balanced chemical equation. Just like having the correct recipe is important in cooking, having the correct balanced equation is important in doing stoichiometry. Your balanced chemical equation is just like your recipe. It will help you understand how to deal with your reactants or ingredients. Again, we cannot do what we need to do or solve the things that we need to solve if our starting procedure, our starting ingredients are not correct. So that's what we need to do first. So for example, right, I have here the skeleton equation for the production of water. So I'm looking at it. We have hydrogen gas combining with oxygen gas, producing your H2O or your liquid water. So let's start with practicing balancing the equation first. I have here a basic chemical equation for the production of water. You have your reactants and then you have your products. In our reactant, we have hydrogen gas combining with oxygen gas, which produces or yields our H2O or liquid water. This doesn't make sense to me just by looking at this, because if I'm looking at it, I have H2, meaning I have two hydrogen atoms in this molecule, and then that's combining with O2, which means there's two oxygen atoms in that molecule, and it produces H2O. In this molecule, I know that I have two hydrogen atoms and one oxygen atom. So why does it not make sense to me? Well, we know that the law of conservation of mass states that whatever you start with should be the same amount that you end up with. We cannot destroy or create something, right? So in my head, if I have two hydrogen here, I should have two hydrogen in the product. If I have two oxygen in my reactant, I should have two oxygens in my product, but that's not what we have here. So this equation is called a skeleton equation. So we have our chemical equation, again, which shows us the production of water, but this is not fully complete. So this is called a skeleton equation because it gives us the bare bones of the reaction, hence the skeleton. So this equation simply tells us your ingredients and the products, but does not tell us the complete process. So this leads us to balancing the equation. So how do we do this? So what you want to do is look at your reactants and your products. So I'm going to start with this. I know that one of my reactant is hydrogen gas. Another reactant that I have is an oxygen gas. And then my products or my product is dihydrogen monoxide or liquid water. So what I'm going to do is I'm just going to count I'm going to look at my reactant side, and then I'm going to compare that to my product side. So I'm going to start with my first ingredient, which is hydrogen gas. In my reactant, I have 2 hydrogen atoms in that molecule, right? And in my product, I have 2 hydrogen atoms. So that makes sense because I'm starting with 2. I should end up with 2. Now I'm going to look at my other reactant, which is my oxygen. I have 2 oxygen atoms on my reactant side in this one molecule of oxygen gas. There's 2 oxygen atoms there. But on my product side, I only have 1 oxygen atom. So again, that does not make sense. So what we need to do is correct this chemical equation so that it tells us the full story of what is actually happening here. So let's start balancing it. The only thing that does not make sense is our 2 oxygen here, and then we have 1 oxygen here. What we need to do is we need to balance that. If I put the coefficient 2 here, that means that I have 2 sets of everything that's here. When I do that, this 2 applies to everything in this molecule. So that means that since I have 2 sets of this whole thing, that gives me 4 hydrogen atoms now and 2 oxygen atoms. So now it balances out the beginning oxygen that I have, right? Before I started with 2 oxygen, now I have 2 oxygen, so now that makes sense. But I changed something here when I put this coefficient 2. When I put this coefficient 2, that also changes the amount of hydrogen that I have. So when I did this, now I have 4 total hydrogen atoms, but in the beginning, in my ingredients, I only have 2 hydrogen atoms. So that means I need to put a coefficient 2 in front of that hydrogen to balance that out. So when I do that, now I have 4 hydrogen atoms here because that you're telling us that you actually needed 2 sets of this hydrogen molecule combining with this 1 molecule of oxygen to produce 2 molecules of H2O or dihydrogen monoxide, which makes sense now because I have 4 hydrogen here, 4 hydrogen here, 2 oxygen here, and then there's 2 total oxygen here, which balances our equation. Just like our recipe, it needs to make sense. So let's practice this. Let's balance our equation. I'll give you a chemical equation. Go ahead and balance it. So let's start with this. So I have diborane 6, generally known as diborane, is the chemical compound consisting of boron and hydrogen, which is our B2H6 right here. It's combining with oxygen gas to produce boric acid and dihydrogen monoxide or water. So go ahead and balance this. This is a skeleton equation. You should know right away that it's not balanced because you have 2 borons over here, but only 1 boron over here. So go ahead and balance it. I will pause the video now and spend about a couple of minutes balancing this equation. Again, start with comparing your reactant, how many you have in the reactant and how many you have in the product. Now that you've spent some time balancing this equation, let's go ahead and look at the correct balance equation here. So you should have started by just looking at how many of each element you have on the reactant side and on the product side. In the beginning, I have 2 borons on my reactant and only 1 boron on my product. So that's a 2 and a 1 here. Then I'm going to look at my hydrogen. I have 6 hydrogens on my reactant. Then I have 1 here and 2 here. So that leaves me with 3 hydrogen atoms on my product. Then the last element that we have is oxygen. I have 2 over here on my reactant. So I'm going to put 2. But on my product, I have 2 here and 1 here. So that leaves me 3. So we can clearly see that this is not balanced because our starting ingredient is not the same as our ending product. And it can't be that way. We need to start by balancing it off. So that means that since I have 2 borons here and only 1 boron here, and since I cannot change that formula because if I added a subscript here, that would change the formula. It won't be boric acid anymore. It would be totally something else. We can't change that. So we need to just put a coefficient in front. So what I'm going to do to balance it is I'm going to put a 2 over here. So that leaves us now with 2 instead of 1. Now I have 2 borons. But like what we did, whenever you put a coefficient, that coefficient applies to everything in that molecule. Once I put this 2 to give me that 2 boron, I also change the amount of hydrogen and oxygen that I have. Now I have 2 hydrogens here and 2 hydrogens here. So instead of 3, now I have 4. But I have 6 in my reactant. So that means that, well, it's still not equal for my hydrogen. So I have to do something here. If I put the coefficient to here, do you guys agree that that leaves us with 4 hydrogen atoms here and 2 here? So now instead of 4, we have 6. Now, instead of it not being balanced, it's actually balanced now, right? So now that leaves us with our last element, which is oxygen. Now, once I put this coefficient to here and coefficient to here, it changes the amount of oxygen we have in the product. So now we don't have 3 anymore. Now we have 4 here and 2 here. So that leaves us with 6, but I only have 2 in my reactant. So that means that I need to put a coefficient 3 here, because if I have 3 sets of this O2 molecule, that gives me 6 total oxygen atoms. I know that I might be going fast for some of you, but I am hoping that you have spent a little bit of time balancing the equation already. So this is pretty much just a review. If I just show you what it's supposed to be, this will now be the balanced chemical equation when you have B2H6 combining with O2, which produces HbO2 and H2O. And now it makes sense. It follows the law of conservation of mass. We have the right amount of atoms in our reactant, which is the same as the amount of atoms in our product side. So now we know that this is a balanced chemical equation. Why is having a balanced chemical equation so important? Again, like what I've been re-emphasizing, a balanced chemical equation is key because it's kind of like our recipe. So again, if I'm comparing it to cooking, just like recipe where it tells us you need a certain ratio between your ingredients to cook and get the right amount of food that you wanted, it's the same thing for our chemical reaction. We need the correct ratio for our ingredients, our reactants to combine to get the right amount of something that we need. So I gave you guys a quick recipe here for rice. For every 1 cup of rice, you need 2 cups of water. So that's a 1-to-2 ratio between the rice and water. If I'm looking at, again, like what we looked at, water. So if we're looking at the balanced chemical equation of water, we know that we need 2 molecules of hydrogen gas combining with 1 molecule of oxygen gas to produce 2 molecules of dihydrogen monoxide or water. Again, it's a 2-to-1 ratio for our reactants or our ingredients to create our product. And this is why our balanced chemical equation is very important. We need to know the right amount of ratio to get a certain product that we want to get. Let's use and write mole ratios first. Let's do this step by step so that we can go ahead and use the full stoichiometry now. So here's an example again of a chemical reaction between 2 gases to produce the gas ammonia. When a nitrogen gas combines with hydrogen gas, it produces ammonia. In this specific chemical equation, which I gave you the balanced chemical equation already, per 1 mole or 1 molecule of nitrogen gas, it needs to combine with 3 moles or 3 molecules of hydrogen gas to produce 2 moles or 2 molecules of your ammonia gas. So again, if I'm just looking at the ratios between my reactant, it's a 1-to-3 ratio between nitrogen and hydrogen. If I'm looking at the ratio between my product and one of the reactants, to get 2 molecules or 2 moles of ammonia or NH3, you need at least 1 mole or 1 molecule of nitrogen gas. And then if I'm looking at, again, one of my reactant to the ratio of the product, if I have 3 molecules or 3 moles of hydrogen gas, you should be able to get at least 2 moles or 2 molecules of ammonia when the reactants combine, right? So these ratios are important because it tells us, well, if I have this amount combining with this amount, you should be able to get this amount. Or if I'm ending with this amount, the ratio of my product should be at least this to this, right? So those ratios are key. So again, let's use this mole-to-mole calculation. If we're looking at our stoichiometry map, I'm looking at the middle portion of it first, where we're going to start with something basic because we've already learned how to convert grams into moles, particles into moles, and volumes into moles in our previous video. So now I'm just going to look at the middle map where we convert moles of your starting point to the moles of what you wanted. Again, we need to use a balanced equation to be able to go from the moles of our given to the moles of our unknown. And this is why this map is important, so that it helps us visualize. Again, if you have this map, then we're just looking at the middle. If you're more of an equation type, and then this is what we're doing. Again, we're starting with our given mole. We're going to use the mole ratio of our given to the wanted based on our balanced chemical equation. And when we do our math, we should be able to calculate our wanted mole. So here's an example, a word problem. So here's a word problem. It's asking us to calculate the number of moles of hydrogen chloride produced from 10 moles of hydrogen gas. Before you do this, let me just tell you a couple of the steps that you should be thinking about as you solve this word problem. The first thing that you should be thinking about is to write down the correct formula and the chemical equation for the reaction that you're getting or for your skeleton equation. So always start with writing down the correct formulas, that's your ingredients, right, and your product, and write down the chemical equation or reaction that's happening there. So make sure that you have the correct ingredients or reactant and the right product. Then you want to balance your chemical equation or balance your skeleton equation. After that, you want to use dimensional analysis to solve the problem from your starting point to what they're asking for or your ending point. And then you always want to wrap it up by asking, does my answer make sense? So let's pause this video now and go ahead and follow these steps. Start with your correct formula and chemical equation for the skeleton equation, then balance that, then use dimensional analysis to solve your problem. After that, does it make sense? All right, so pause your video now. So you probably started doing this. If you are having some problems, it's okay. We'll walk through this together. This is our first example. So again, we want to start with writing down the correct formula and chemical equation for the skeleton equation. They said here that we're looking for the moles of hydrogen chloride produced. So the key word here is produce. That means that hydrogen chloride is our product because that is what is being produced. If we are ending with hydrogen chloride, that means that our 2 ingredients must be hydrogen and the other one must be chlorine, because you can't end up with hydrogen chloride if you don't have hydrogen and chlorine. I know my reactants has to be hydrogen gas and chlorine gas. Our product should be hydrogen chloride. Hydrogen chloride is a ionic compound, so you should be able to balance their charges there because all ionic compounds are neutral. So this is my skeleton equation. Why is it H2 and why is it Cl2? Right? On your cheat sheet, when you're looking at the common polyatomic ions, we know that hydrogen gas and chlorine gas cannot be by themselves. They are one of the common diatomic molecules, meaning that they're too needy. They can't be by themselves most of the time or naturally. So they would always cling on to one of their same kind. So this is why it's H2 and Cl2. Now that we have our skeleton equation, you should have balanced it. So again, start by writing down the elements on your reactant side and write down the elements on the product side and count how many of each you have on each side. Now that we've written down our skeleton equation, we need to balance it. I have 2 hydrogens on my reactant side, but I only have 1 hydrogen on my product side. So that means that I need to put 2 for the coefficient, because now you're telling us that you have 2 sets of these. Again, we cannot just put a 2 down here because it's not hydrochloric acid anymore or hydrogen chloride. If you put that 2, it becomes totally something else. So we cannot change the formula, because if you do, you're turning it into something different. We can only add coefficients where we say you have this many sets of this molecule or compound that you have. So we can't do that. So we can only put that 2. Now my hydrogen is balanced because I have 2 hydrogen on my reactant and I have 2 hydrogen on my product. Now I'm going to look at my other ingredient, which is chlorine. I have 2 chlorine atoms here in this 1 molecule of chlorine gas. I have 1 chlorine atom here, but since I put the 2 for the coefficient, that means that I have 2 sets of these, making it 2 atoms of chlorine. So now everything is balanced. My balance equation is 1 mole or 1 molecule of hydrogen gas combining with 1 mole or 1 molecule of chlorine gas produces 2 moles or 2 molecules of hydrochloric acid or hydrogen chloride. So now that we have balanced it, we can move on to our dimensional analysis to solve the problem. So now we're looking at the balance. We balanced the equation. Now we're using dimensional analysis to solve the problem. I know that I'm starting with 10 moles of hydrogen gas. How do I know that? Well, it says here on the problem that you have 10 moles of hydrogen. So I'm going to put 10 moles of hydrogen here. Now I need to put the mole ratio of what I have to what I'm looking for. I have hydrogen, so I know that I want to put hydrogen here, moles of hydrogen down here, and then I want to put moles of whatever I'm looking for up here. I'm looking for hydrogen chloride or hydrochloric acid, so HCl should be up here. So how do I get the mole ratio? I just need to look at my balanced chemical equation and look at the numbers, the coefficients that we put in that. So there's no number in front of the hydrogen, so that means I have at least 1. So I have 1 mole of hydrogen gas. Now I'm going to look for my HCl or hydrochloric acid or my hydrogen chloride. It's right here. I have 2 in front of it, so that means that I have 2 moles of that. So now we can just do the math. For every 10 moles of hydrogen gas, right, you multiply that to 2 moles of hydrochloric acid or hydrogen chloride divided by 1, because again, this is our ratio. That should leave us with 20 moles of hydrochloric acid. You have to ask yourself, does your answer make sense? Well, if I'm looking at the ratio, for every 1 mole of hydrogen, it should produce 2 moles of hydrochloric acid or hydrogen chloride. It sort of makes sense. If I'm starting with 10, I just need to double that because the ratio is 1 to 2. So that means that I should end up with 20 moles of hydrochloric acid or hydrogen chloride. Now that we've done that, I want you to practice to see what you've learned. So I'm going to give you another word problem. So here's a problem for you. Calculate the number of moles of chlorine needed to form 14 moles of iron 3 chloride. Pause the video now, but again, remember the steps that you need to take. Again, start with writing down the correct formulas and chemical equation for the skeleton equation. After that, balance your equation, then use dimensional analysis from what you're given to what you're looking for. And then after that, make sure that you ask yourself, does it make sense? So pause the video now and do it on your own. Your skeleton equation should have looked something like this, where you have iron, which is usually in a solid state, combining with chlorine gas, which we know is Cl2 because it's one of those diatomic gases, which produces iron 3 chloride, where the formula is FeCl3. So that is our skeleton equation. After that, you should have balanced the equation. If you have not balanced it yet, go ahead and go balance that right now. Your balanced chemical equation should be now 2Fe, 2 moles of iron, combining with 3 moles of chlorine gas, producing 2 moles of iron 3 chloride. So that's our balanced equation. Then I'm going to do the dimensional analysis. I know that I'm starting with 14 moles of iron 3 chloride because that's what it says in the problem. If I have 14 moles of iron 3 chloride, or if I needed 14 moles of iron 3 chloride, how much chlorine gas should I use? So starting with 14 moles of iron 3 chloride, I know that my ratio of what I have to what I'm looking for is a 2 to 3 ratio, right? Again, what I have to what I'm looking for, so that's a 2 to 3. Where did I get these numbers from? 2 moles of FeCl3. So I'm going to put 2 moles of FeCl3 right here. And then where I got this 3 from is from the balance equation, which is right here. It says that I have 3 moles of chlorine gas. So I'm going to put 3 moles of chlorine gas here. I just need to do the math. 14 times 3 divided by 2. That should give you 21 moles of chlorine gas. So that should be your final answer. Does it make sense? Well, if it's a 2 to 3 ratio between your product to one of your ingredients, does it make sense? Well, if I have 14 moles of FeCl3, that should be my 2. That means that, well, if I just divide 14 by 2, that's 7 and 7. So that means if I have another 7, that should be what my answer should look like. So 21 makes sense to me because, again, that's how I just break it down. If it's a 2 to 3 ratio and my 2 is 14, so that means that if I divide that into 2, it's 7 and 7. So that means that my 3 should be 7, 7, and 7. So that should equal to 21. It makes sense. That's just me. Let's do more just to practice. Here's a word problem for you. How many moles of water or H2O are produced from 15.64 moles of O2? Go ahead and pause the video. Remember the steps that you need to take. Go ahead and pause this video now. After a couple of seconds, I will show you the answer. Now that you've spent some time following the steps here, you should have started with your skeleton equation, then balancing that. So I'm going to combine the first 2 steps. So this is our balanced chemical equation. From our skeleton equation, you should have 2 moles of hydrogen gas combining with 1 mole of oxygen gas, producing 2 moles of H2O or water. That's our balanced chemical equation. Now that we have our balanced chemical equation, should be able to do the stoichiometry part or the dimensional analysis part. 15.64 moles of oxygen gas, which is what we're starting with. I am going to multiply that to the mole ratio of what I have to what I'm looking for. What I have is oxygen, so I'm going to put that on the bottom to cancel out that unit. And then I'm left with the unit that I do want, which is moles of H2O, which is what I'm looking for. So I just need to do the math. 15.64 times 2 divided by 1, that gives us 31.28 moles of H2O or water. Does it make sense? It's a 1 to 2 ratio. So that means that if my moles of oxygen is my 1, I just need to double that and I would get how many water it should be producing. So 15.64 times 2 is 31.28. It makes sense because it's doubled. Since it's a 1 to 2 ratio, it just makes sense to me. With that said, hopefully going from mole to mole, from your given mole to your wanted mole is understood. If it's not understood, please rewind the video and go ahead and watch it again. But for now, let's move on to some of the more complex dimensional analysis process. So I'm going to start with our mass to mass calculation. If I'm looking at the mole map, or I'm sorry, the stoichiometry map, I'm going from a given mass. I'm going to go convert that mass into mole, then convert that given mole into the moles of what I want. then convert that to the mass that they're looking for. So if I'm going to follow the map, I'm going to go from here to here, then from there to there, then lastly from here to there. If you're following this map, or if you're using this map, we're just going from here to here to here, right? If you're more of an equation-based person, then this is what we're doing. If we're mapping it out in our head, we're going to go with your starting mass, convert that into your mole by using this mole, this conversion factor. Now that we have that in mole, we can multiply that to the mole ratio of what we want, what we have to what we want. Now that we have the moles of what we want, we can now convert that into the mass of what we want. So that means that you need your periodic table here, because to convert mass to mole, you need to find the molar mass of something, and to convert moles to mass, you need to find the molar mass of something. All right, so let's start with this. Let's go and practice by doing this one word problem. Right, it says right here, calculate the mass of oxygen produced from the decomposition of 75.0 grams of potassium chlorate. With all word problems, we need to follow, systematically follow step-by-step procedure. So again, we're using the same thing. Start with writing down the correct formulas and chemical equation for the skeleton equation. After that, we need to balance the equation. Then after that, we can use the dimensional analysis steps to solve our problem. So let's start with writing down our skeleton equation. I know that this reaction is a decomposition reaction. So that means that I have one reactant breaking down into many products. So what is my reactant? Well, it says that what's decomposing, or what's breaking down. They said that potassium chlorate is what's breaking down. And when they break down, it produces at least oxygen. But we know that if you have potassium and chlorate, you should have more than just one product here, not just oxygen. You should have at least two products there. So when potassium chlorate breaks down, you get potassium chloride and oxygen gas. If you don't know what the products are, again, you can simply Google it, or if you've done this so many times and you know how it works, then go ahead and do that in your head. But if you are unsure, or if you don't know what the products are, make sure that you use the tools that you have to see what they are, or double check your work by going to Google. So now that we have the skeleton equation, we should be able to balance it. Again, compare your reactants to your products. In this case, I would have my balance equation should be 2 potassium chlorate breaking down into 2 moles of potassium chloride and 3 moles of oxygen gas. How did I get that? Well, I have potassium, I have chlorine, and I have oxygen on my reactant. I have potassium, chlorine, and oxygen on my product. If I just look at how many initial potassium I have 1 here, and then I have 1 chlorine, and then I have 3 oxygen to begin with, right? And then in my product side, I have 1 potassium, 1 chlorine, and then 2 oxygen here. Initially, potassium and chlorine are balanced, but your oxygen is not. And then, so that means that we need to balance that somehow. So that means that, well, the least common multiple of 3 and 2 is 6. So that means that, well, how can I get 6 on this side? If I multiply this by 2, I get 6. If I multiply this by 3, I get 6. So that means that I need to put 3 here to get that 6. And that means that I need to put 2 here to get that 6. When I put the 2 in front right here, I change the amount of potassium that I have to 2, and that chlorine now is 2. So that means that I have to put 2 here to change this to 2 and 2. Now that I have the balanced equation, I can just do my dimensional analysis. Again, if I'm going to map this out in my head, I have my given mass. I need to convert that given mass into mole first. After I converted that into mole, I don't want potassium chlorate, I want oxygen. So I need to use a mole ratio of my given to my wanted so that I can get moles of oxygen, but I don't want moles of oxygen. They're asking you for mass of oxygen. So that means that I need to do this one last conversion right here, converting that mole into mass. And that should give me my mass of oxygen. So again, that's me mapping it out. Like what I said, we need the periodic table here because for us to convert this mass of potassium chlorate into moles of potassium chlorate, we need to look at the molar mass of this potassium chlorate. So in the periodic table, right, each potassium is about 39.098 grams. I have one of them. So the total mass of that potassium is 39.098. Chlorine, each atom weighs about 35.45 grams. I only have one. So total is 35.45. But my oxygen, I have three of them, and each of those oxygen is 15.999 grams. So total times 3 is 47.997. So if I just add up 47.997 plus 35.45 plus 39.098, that gives me 122.549 grams of potassium chlorate per 1 mole of potassium chlorate. So that's my mole ratio, my mole to mass, or my mass to mole conversion here. So when I do my math, this will cancel out. Now I'm left with moles of potassium chlorate, but I don't want moles of potassium chlorate. So that means that I'm going to put potassium chlorate down here, and I'm looking for oxygen. So I'm just going to look at the coefficient based on my balanced chemical equation. I have 2 moles of potassium chlorate, so I'm going to put 2 moles of potassium chlorate down here. And then I have 3 moles of oxygen gas, so I'm going to put 3 moles of oxygen gas right here. Why did I do that? Well, I have moles of potassium chlorate right now. I don't want that. I want to get rid of that. So I'm going to put that on the bottom here. When your numerator and your denominator is exactly the same, the units are exactly the same, you can cancel out those units. So now I'm left with moles of oxygen. But I don't want moles of oxygen. I want mass of oxygen. So that means I need to do one last conversion factor, right? We know that each oxygen is 15.999. I have 2 of them in O2. So that means that the total mass is 31.998 grams. Now, when I do this moles of oxygen cancel out that moles of oxygen. I'm left with the unit that I do want, which is grams of O2. Now I can just do my math because I'm left with the unit that I do want in the end. So I'm going to go 75.0 times 1 divided by 122.549 times 3 divided by 2 times 31.998 divided by 1. That should give you your final answer. So our final answer should be 29.4 grams of oxygen gas. So when you have 75.0 grams of potassium chlorate breaking down, you should get, or you should be able to collect at least 29.4 grams of oxygen gas. So this is what this equation or this problem is letting us know. We went from mass of our given to the mass of what we want. So I want to give you some practice here. Here's the word problem that I want you to work on. Make sure that you follow these steps, but it says right here, when B2H6 combines with O2, it produces HbO2 and H2O. So what is the mass of HbO2 produced from 196.5 grams of B2H6? Always start with writing down your skeleton equation, then balance that, then do your dimensional analysis. So again, pause your video, go ahead and work on this problem. Your skeleton equation should have been B2H6 plus O2, because it says here when B2H6 combines with O2, so that's our reactant. Those are our 2 ingredients. Produces, so that means you have to put an arrow. What is it producing? It's producing HbO2 and H2O. So this is why those are our products. So that's our skeleton equation, but we know that it's not balanced because looking at the first element, I have 2 borons here and only 1 here. I know right away that it's not balanced. So balance it. When you balanced it, hopefully you've gotten a ratio of 1 to 3 in our reactants. So 1 molecule or 1 mole of B2H6, and then 3 moles of O2, which produces 2 moles of HbO2 and 2 moles of H2O. So that's our balance equation. Now that you've balanced the equation, hopefully you've mapped it out in your head. Since we're going from mass to mass, you know that you needed your periodic table to find the molar mass of something. So the molar mass of B2H6 is 27.668 grams. How did I get that? Well, you need to find the mass of boron and hydrogen. Each boron is 10.81 grams. You have 2 of that. So total, you have 21.62. Each hydrogen is 1.0080. Since you have 6 of that, the total is 6.048. So combining those 2 should be 27.668 grams of B2H6. And then we want to put that 1 mole on top because we want to convert that grams, that mass, which is in grams right now, into mole. So this is the conversion factor that we need, but we don't want to end up with moles of B2H6. So we need to do a mole ratio of what we have to what we want. Your mole ratio should have been 1 mole of B2H6 because there's no number here. So you have at least 1. And then your HBO, you have 2 of them. So I'm going to put 2 moles of HBO right here. So we know that it should be a 1 to 2 ratio. Our math should be pretty easy here. But then we don't want to end up with moles of HBO2. We want to end up with mass of HBO2 in the unit of grams. So that means that we need to look for the molar mass of HBO2. So per every mole of HBO2, you should have the mass of 43.816 grams. How did I get that? Again, boron and hydrogen, we already found out how much they weigh. Each oxygen is 15.999. You have 2 of them, so that's equal to 31.998 grams, plus your 1 hydrogen, which is 1.0080 grams, plus your 1 boron, which is 10.81 grams. So total 43.816. Now that I'm left with the unit that I do want, which is grams of HBO2, I can just do my math. 196.5 times 1 divided by 27.668 times 2 divided by 1 times 43.816 divided by 1. That should leave us with your final answer. Your final answer, your calculator should have given you a big number like this. But again, following the correct significant figure, since we're only starting with 4 numbers here, we should only end up with 4 numbers here, right? Because we can only be as detailed as our initial measurement. This 622.3683,678, we only need the first 4. So that should be 622.4 grams of HbO2. With that said, let's move on to the next step, which is representative particles to representative particles. So if I'm looking at your stoichiometry map, I'm looking at the middle portion here. I'm starting with particles, converting that into moles, then mole to mole ratio, like what we have been doing, then converting that mole to representative particle. If you're using this mole map, then this is where we are going. If you're more of an equation-based person, this is what we are doing. We're going from representative particles of your given, converting that representative particle of your given to moles, then multiplying that moles of your given to the mole ratio of what you have to what you're looking for. But since we don't want to end up with the moles of what you're looking for, we need to multiply it to, again, Avogadro's number. That would give us representative particles. There's an extra step here. Again, if you're looking for an atom, you need to just multiply how many atoms of that specific element or particle you are looking for. Let's do a practice problem. The problem is asking you to calculate the amount of formula units of magnesium chloride produced from the synthesis or the combination reaction of 2.86 times 10 to the 24 molecules of chlorine gas. Follow these steps. Go ahead and pause the video now. write down the skeleton equation first with the correct formulas. Then after that, balance it. After that, go ahead and use your dimensional analysis skill to solve the problem. Your skeleton equation should look somewhat like this. You're combining magnesium, which is a metal, so put solid there. Combining that with chlorine gas, we know that that's one of the diatomic gases, which produces magnesium chloride, which is MgCl2. Again, that's an ionic compound. Magnesium is losing 2 electrons. Chlorine only needs 1 electron to complete its octet. And this is why the ratio when they combine is a 1-to-2 ratio. So this is our skeleton equation. We need to balance it because this is incomplete. So when you balance it, you should see that it is already a balanced equation. Our skeleton equation does not need to be changed, which makes it our balanced chemical equation already. So this should make it pretty simple for what we are trying to do. So let's start with doing our dimensional analysis. Right, let's start with the given. You're given 2.86 times 10 to the 24th molecules of chlorine gas. So I'm starting with that. If I'm mapping it out in my head, I know that I need to convert that representative particles into moles. After that, I need to multiply to the mole ratio of what I have to what I want. Then after that, I need to convert that mole of my wanted to the representative particles of what I want. So put this as your first dimensional analysis conversion factor. For every 1 mole of chlorine gas, we know that that has about 6.02 times 10 to the 23rd molecules of chlorine gas. Again, Avogadro's number, but we don't want to end up with moles of chlorine. We want the formula unit of magnesium chloride. So I need to do the mole ratio of what I have, which is chlorine. So that should be going in the bottom. And then magnesium chloride on the top, which is what I'm looking for, which is a 1-to-1 ratio, right? So that means that I just need to convert that mole into representative particles or formula unit of magnesium chloride. So that means that I need to put 6.02 times 10 to the 23rd formula unit of magnesium chloride per every 1 mole of magnesium chloride. This should make it pretty easy because if you're just looking at the problem, this molecules of chlorine cancels out, moles of chlorine cancels out, moles of magnesium chloride cancels out. I'm left with the formula unit of magnesium chloride. If I'm looking at the math, it's just going to be 2.86 times 10 to the 24th times 1 divided by 6.02 times 10 to the 23rd times 1 times 1 times 6.02 times 10 to the 23rd divided by 1. Again, if you have a number that's on your numerator and denominator that's exactly the same, that equals to 1. Anything divided by or multiplied by 1 is the same exact number. So our final answer should be 2.86 times 10 to the 24th formula units of magnesium chloride. Since it's a 1-to-1 ratio, it makes sense that, well, if this is my starting, I should have the same amount of my product because it's a 1-to-1 ratio. So if I'm starting with 2.86 times 10 to the 24th, I should end up with 2.86 times 10 to the 24th. So let's do another one just to make sure that this is sinking in. Here's another word problem. It says calculate the amount of atoms of oxygen gas produced from the combustion reaction of 8.86 times 10 to the 27 molecules of ethane gas, which is the formula is C2H6. So we have a combustion reaction. Follow your steps. Pause your video now. Go ahead and write down your skeleton equation first based on this word problem. Then balance that chemical equation. Then use your dimensional analysis skill to solve what they're asking for. After spending some time doing this problem, you should end up with a skeleton equation of C2H6 combining with O2, which produces CO2 and H2O. I know that the H2O was not mentioned in the word problem, but you know that in every combustion, complete combustion, it always produces carbon dioxide and water. So hopefully you added the H2O there. So this is our skeleton equation. Now we need to balance it because right now it is not a balanced chemical equation. When you balanced it, this is the balanced equation that you should have ended up with. you should have gotten 2 moles of C2H6 combining with 7 moles of O2, which produces 4 moles of CO2 and 6 moles of H2O. So that is our balance equation. Now that we have our balance equation, we should be able to do our dimensional analysis. Again, start with what you are given, map it out in your head, right? You want to convert that representative particles into mole. You don't want that given mole, so you want to do the mole ratio of your given to what you want, but you don't want the moles of what you want. They want atoms, so you want to convert that mole of what you want to the representative particles of what you want, but then there's an extra step here because we are looking for oxygen, right? So this is how your work should have looked like. I know if you did not finish it yet, pause the video now and go ahead and try to do this. But for those that have done the problems already, this is what it should look like, right? The first conversion factor should have been 1 mole of C2H6 over 6.02 times 10 to the 23rd molecules of C2H6. That converts our molecules into mole, but we don't want mole of C2H6. So we want the mole ratio of what we have to what we want. So that means that the moles of C2H6 should be on the denominator and the mole of CO2 should be on the numerator because that's what we're looking for, right? So if I'm looking at the balance equation, I have 2 moles of C2H6. So I'm going to put 2 moles of C2H6, and then I have 4 moles of CO2. So I'm going to put 4 moles of CO2 here. I don't want moles of CO2. I want atoms of oxygen in my CO2. So that means I need to go and use another conversion factor. To get rid of this mole of CO2, I need to put 1 mole of CO2 on the bottom. There's 6.02 times 10 to the 23rd molecules of CO2 in 1 mole of CO2, but I want specifically oxygen gas from that molecule of carbon dioxide, right? So that means that if I'm looking at one molecule of CO2, I have 2 atoms of oxygen atom in that molecule. So I need to do that one last step. So if I'm following this, molecules of C2H6 cancels out, mole of C2H6 cancels out, mole of CO2 cancels out, molecules of CO2 cancels out. Now I'm left with the unit that I do want, which is atoms of oxygen. Now I can just do my math. 8.86 times 10 to the 27 times 1 divided by 6.02 times 10 to the 23rd times 4 divided by 2 times 6.02 times 10 to the 23rd divided by 1 times 2 should give us our final answer. Again, to make it simple, since you have the same number on your denominator and your numerator, right, that technically equals to 1, it simplifies itself. So now literally all I have to do is 8.86 times 10 to the 27 times 1 times 4 divided by 2 divided by 1 times 2 divided by 1. That should give me my final answer. My final answer should be 3.54 times 10 to the 28 atoms of O2. I know your calculator might have given you a big number here, but we need to put the right amount of significant figure and put in the correct scientific notation. Since I started with 3 numbers here, I should only end up with 3 numbers here. And again, we need to put in the correct scientific notation. So the final answer should be 3.54 times 10 to the 28. Mapping it out, this is what we did. I want to give you some time to practice some more. So here are some word problems that I want you to do. But before that, again, always follow your steps. So here's 2 word problems that I want you to do. The first problem is asking you, how many atoms of oxygen in water is produced when hydrogen gas and 2.86 times 10 to the 24 molecules of oxygen gas combines or synthesize? The second problem is, how many molecules of chlorine gas are produced when 2.594 times 10 to the 20 molecules of hydrogen chloride or hydrochloric acid decomposes? So pause the video now and go ahead and spend some time working on these 2 problems. After a couple of seconds, I would show you the correct answer for both the problem. I'm going to start with the first problem. Your skeleton equation should have looked something like this. H2, which is a molecule of hydrogen, combining with oxygen produces H2O. We did this before. So hopefully you were just looking at your notes and you should know the skeleton equation. The balanced equation should have looked like this. 2 moles of hydrogen combining with 1 mole of oxygen produces 2 moles of H2O. The final answer should have been 5.72 times 10 to the 24th atoms of oxygen, right? Not O2 anymore, since we're looking for atom of oxygen is just atoms of O. So again, in 2.86 times 10 to the 24 molecules of oxygen gas, you should get 5.72 times 10 to the 24th atoms of oxygen. The second problem, right, is asking us for how many molecules of chlorine gas are produced when you have 2.594 times 10 to the 20th molecules of hydrogen chloride or hydrochloric acid. Your skeleton equation should have looked something like this, right? This is not balanced. Your balanced chemical equation should have looked something like this. And your final answer, when you did it, should have been 1.297 times 10 to the 20th molecules of chlorine gas. Again, I have to base my answer on the correct significant figure and scientific notation. This is why I only have 4 numbers in 1.297 there. Now that we're done with mass to mass, I want to go over the last portion of our stoichiometry map, which is our volume to volume calculation. If we're looking at our stoichiometry map, we are now looking at volume, given volume to moles, then mole to mole ratio, then converting that back into a volume of what we're looking for. If you're looking at this map, this is where we're going. If you're more of an equation type of person, then this is the equations that we're using. Again, volumes to mole, mole to mole, then mole to volume is what we're doing. So here's an example. Word problem, it says calculate the volume of oxygen gas in milliliters. So they wanted us to do it in a specific unit, produced from the decomposition of 4.00 liters of nitrogen dioxide happening at standard temperature and pressure. Same process, right? We want to start with our skeleton equation, balancing that, then using dimensional analysis to solve the problem. Then after that, just double checking our answer, does it make sense? So let's start with our skeleton equation. We know that there's a decomposition happening here. So that means we only have one reactant or one reactant producing many product, right? So since we're starting with nitrogen dioxide, which consists of nitrogen and oxygen, that means that our product should have at least 2 things. Our skeleton equation should look something like this. Again, when nitrogen dioxide breaks down, it breaks down into nitrogen gas and oxygen gas. Both nitrogen and oxygen are diatomic molecules. They cannot be by themselves. That's why it's N2 and O2. It's not balanced, so we need to balance this like what we have been doing. You want to compare how many atoms in your reactant to how many atoms in your product. When you balance it, it should look somewhat like this. If you haven't done it yet, go ahead and pause your video and balance it at first. Now that you've balanced the equation, this is the answer that you should have gotten. You should have gotten 2 moles of NO2, producing 1 mole of nitrogen gas and 2 moles of oxygen gas. Now that we have the balanced equation, we can use our dimensional analysis skill to solve for what they are asking us for. We're starting with 4.00 liters of nitrogen dioxide. So I'm starting with that. I want to end up with milliliters of O2 because they wanted that in milliliters in the word problem. So I know that I need to go from volume to mole to mole ratio of moles of what I have to moles of what I'm looking for. I don't want to end up with moles of what I'm looking for. So I need to do a couple more conversion of volume, a mole to volume. Then this would give me the unit liters, and I don't want liters, so I need to do another conversion of liters to milliliters. So let's just fill this up. If you have not done it yet, go ahead and pause the video real quick, solve the problem. After a couple of seconds, I would show you the answer. Now that you spent some time working on this on your own, I'm just going to start filling up some of these conversion factors. So again, my first conversion factor should have been 22.4 liters on the bottom, and I know that that's per mole. So 1 mole of NO2 takes up about 22.4 liters. Where did I get that 22.4 liters? It's in our map. We know that for every 1 mole of any substance at standard temperature and pressure, it will always take up 22.4 liters. That's our molar volume. So now that I have moles of NO2, I don't want moles of NO2, I want moles of O2. So that means I need to do the mole ratio of my given to want. So I'm looking at the balanced equation. I know that I have 2 moles of NO2. I'm looking at the oxygen. I have 2 moles of oxygen. So it's a 2-to-2 ratio. I don't want to end up with moles of O2. So I need to convert that moles into volume. So that means I want to put moles on the bottom to cancel out that moles of O2. And I have to put 22.4 liters of oxygen on the top because that's the molar volume. But I don't want liters, I want milliliters. So I need to do one last conversion. I know that 1 liter of oxygen is the same thing as 1,000 milliliters of oxygen. Now I just need to do my math. Before that, I want to make this a little bit more simpler. I have 22.4 here on the numerator, and I have 22.4 on the denominator. You know that when you have 2 numbers that's exactly the same on the numerator and the denominator, that just equals to 1. I don't really need to worry about that. So now I just need to do my math. 4.00 times 1 times 2 divided by 2 divided by 1 times 1,000 divided by 1, you should have our final answer. So our final answer should be 4,000 milliliters, right? But since we have 3 significant figures in our starting unit, we can't just leave it as 4,000 because 4,000 milliliters has only 1 significant figure. So we need to put this in scientific notation. So our final answer should be 4.00 times 10 to the third milliliters of O2. If you are following the map, this is what we did. Again, fairly simple, right? I think the most complex one should be the mass to mass, because you need to look at the periodic table for the molar mass of something. Volume to volume is fairly easy, and representative particles to representative particles should be fairly easy too. Let's do some practice problems here. I'm going to give you 2 problems that you can do on your own. The first one is asking you for how many milliliters of fluorine gas will be needed when the experiment allows it to combine with hydrogen gas to produce 6 liters of hydrogen fluoride or hydrofluoric acid at standard temperature and pressure. The second question is, how many liters of tricarbon octahydride or propane gas are produced when 3 liters of hydrogen gas combines with carbon at standard temperature and pressure? So pause the video, work on the first problem first, then work on the second problem. Don't forget the procedures that we always follow. Start with your skeleton equation, balance that chemical equation, do your dimensional analysis process, then ask yourself, does my answer make sense? So pause the video and solve these problems. So you should have finished solving both the problems now. I'm going to start with the first problem here. The skeleton equation for the first problem should have looked something like this, where you have hydrogen gas combining with fluorine gas, which produces hydrofluoric acid, which is in the liquid state. Hydrogen and fluorine are both diatomic molecules where they can't be by themselves. So that's why it's H2 and F2. And then it produces HF or hydrofluoric acid. We can tell right away that it's not a balanced equation. When you balanced it, it should have looked something like this, which is now 1 mole of H2 combining 1 mole of fluorine gas produces 2 moles of hydrofluoric acid. Now that we have that, your dimensional analysis should have looked something like this. You should have started with 6 liters of hydrofluoric acid. You should have converted that volume into mole, but you don't want mole of your given. You want moles of what you're looking for or you're wanted. So you should have multiplied it to the mole ratio of what you have to what you're looking for. but you don't want moles of what you're looking for. You want volume of what you're looking for. So you should have multiplied it to this conversion factor, which gives us liter. But the problem is asking us for milliliters. So you should have done another step of converting that liters into milliliters. When you do the whole math, you should have gotten 3,000 milliliters of fluorine gas, which has one significant figure. We only started with one significant figure. So I could have just left it as that at 3,000 milliliters of fluorine gas. So that's the answer for the first problem. Now, the second problem, your skeleton equation should have looked something like this, where it says that you have carbon combining with hydrogen gas to produce propane, right, which is C3H8. So you have 1 mole right now, C plus H2 produces C3H8. Again, H2 is a diatomic molecule. That's why it's H2. So now we know that this is not balanced because I only have 1 carbon in my reactant, but 3 carbons in my product side. So that means that I need to add some coefficients right here. So your balanced equation should have been 3 moles of carbon combining 4 moles of hydrogen, which produces 1 mole of C3H8 or propane. Now that we have the balanced equation, you should be able to do your dimensional analysis, converting that volume into moles, mole to mole ratio of what you have to what you're looking for, then converting that mole of what you're looking for to volume of what you're looking for. When you do the math, you should have gotten 0.75 liters of C2H8, but C3H8, that's a typo, right? I only have 1 significant figure in my starting number. So that means I should have 1 number or 1 significant figure in my final answer. So the final answer should be 0.8 liters of C3H8. So using your stoichiometry map and using your dimensional analysis skill, we should now be able to do a little bit more of a complex problem. So far, we've just been going from one unit to another specific unit. You might start with mass, and then they might want you to end up with some volume. So let's go ahead and do that. Let's try to make this a little bit more interesting. Let's try to base it on what's going on around our environment now. So let's look at climate change and greenhouse gases using this stoichiometry map and the dimensional analysis concept that we've learned. We should be able to kind of figure out how we're affecting our environment through these greenhouse gases. Again, using this stoichiometry map and the dimensional analysis skill, we should be able to predict practical amounts of something. This is what we're going to do. We're going to learn how to calculate the actual amount in mass and volume of greenhouse gases that we release into our atmosphere due to a combustion reaction. So we know that when something is catching on fire, which requires oxygen, it most of the time, if it's a complete combustion, produces carbon dioxide and water, they're both greenhouse gases. Burning a candle releases 2 greenhouse gases into our atmosphere. It releases carbon dioxide and water, which is, again, 2 of the greenhouse gases that we know. To do a small scale example of how we are affecting the environment, we performed an experiment in class where we use a candle to see how much of these greenhouse gases we actually release into the atmosphere. I had a candle. The mass of that candle initially, before we light it up or before it started burning, is about 18.2 grams. After letting it burn for a couple of minutes, right, the final mass of that candle is 15.9 grams. That means that if we're starting with 18.2 and we ended up with 15.9, that means that we've used up 2.3 grams of wax in that candle. We've used up about 2.3 grams. So knowing this, we should be able to figure out how much carbon dioxide and water molecules we've actually released into the atmosphere, which is, again, a greenhouse gas, which causes our atmosphere to heat up a little bit more. Make sure that you remember the steps that we take. Always start with your skeleton equation, then balancing it, then using dimensional analysis. So our skeleton equation should look somewhat like this. we know that paraffin wax, which the formula is C25H52, which is in the solid state. In a combustion, it always combines with oxygen, so plus O2, which is in the gas form, which produces carbon dioxide gas and water vapor. This is our skeleton equation. We know right now that it is not balanced because we have 25 carbon here and only 1 carbon there. Right away, we know that it's not balanced. So go ahead and balance the equation first. After you balance it, I will move on. So pause the video right now and balance the equation for this combustion reaction. You should have spent some time balancing the equation. If you have not, please try your best to balance it. If you have, this is the balanced equation that you should have ended up with. You should have ended up with 1 mole of C25H52 combining with 38 moles of O2 gas, which produces 25 moles of carbon dioxide and 26 moles of H2O gas. So that's our balanced equation. Now we can use our dimensional analysis skill. We know that we're starting with 2.3 grams of paraffin wax, which is C25H52. And then we want to end up with volume and mass of carbon dioxide and water. So I'm starting with carbon dioxide first. I'm going to find the mass of carbon dioxide that this 2.3 grams of C25H52 actually release, right? So pause the video right now. Go ahead, map it out. I'm not going to let you know how many steps or conversion factors are needed here. I wanted to do it, you to do it on your own. Pause the video, all right? And after a couple of seconds, I will show you what your dimensional analysis should have looked like. Now that you spent some time doing the problem, this is what your dimensional analysis should have looked like. So you should have converted that grams into moles first. So that means that you needed your periodic table to find the molar mass of C25H52. The molar mass of C25H52 is 352.441 grams. How did I get that? You have 25 atoms of carbon and 52 atoms of hydrogen. How many total carbons do I have? In the mass of 25 carbon is about 300.025. The mass of 52 hydrogen is 52.416. You combine that together, this is where you get 352.441 grams. Now that I have moles of C25H52, I don't want moles of C25H52, so I need to do a mole ratio of what I have to what I'm looking for. So C25H52 goes on the denominator because that will cancel out this mole. Then mole of CO2 should go on the top because that's what I'm looking for. So where did I get the 25 from? And this one, I know that I have 1 mole of C25H52, so I'm just going to put 1 mole here. I have 25 moles of CO2, so I'm going to put 25 moles of CO2 up here. When I do that, I'm left with moles of CO2, but I don't want moles of CO2. So my next conversion factor, I need to convert that moles into mass. This mole of CO2 cancels out that mole of CO2. The mass of 1 mole of CO2 is 43.999 grams. How did I get that? 1 atom of carbon is 12.001. Each oxygen is 15.999. I have 2 of them, so that means that that's 31.998 grams. Add the 2, you get 43.999 grams. Now that I'm left with a unit that I do want, which is grams of CO2, I can just do the math. I go 2.3 times 1 divided by 352.441 grams times 25 divided by 1 times 43.999. That should give you the number 7.1783326 grams of carbon dioxide, but I'm only starting with 2 significant figures. So that means that I only need the first 2 number. I have to look at the third number here to see if I needed to round up my last estimated number. I do, because 5 and above, you round up. 4 below, you let it go. Since this is 5 and above, I need to round that up. So my final answer should be 7.2 grams of carbon dioxide. That's not that much, 7.2 grams, right? Like, That's kind of little. So that's how many mass of that's the mass of carbon dioxide that's being released when 2.3 grams of C25H52 is released into the atmosphere or burns. There you go. Now let's look at volume of CO2. Dimensional analysis. Again, we already have our balanced equation. We're still starting with 2.3 grams of C25H52. Now we want to end up with liters of CO2. So go ahead and pause your video, right, and do your dimensional analysis here. And after a couple of seconds, I will show you how I did it. Now that you spent some time doing this, this is what your dimensional analysis should have looked like. Again, we need to convert that grams into mole. We did that in the previous step. So I know that it's 352.441 grams. Now that I have moles of C25H52, I need to do the mole ratio of what I have to what I'm looking for. This cancels that out. Then my mole ratio will cancel out that C25H52, which leaves me with moles of CO2. I have 25 moles of CO2. Where did I get that? Again, from the balanced chemical equation, they said that your ratio is 1 to 25. So this is why I put 25 there. But I don't want to end up with moles of CO2. So I'm going to convert that moles into volume. So I need to go 22.4 over 1 mole, because now this mole of CO2 cancels out that mole of CO2. I'm left with the unit that I do want, which is liters of CO2. Now that I'm left with the unit that I do want, I just need to do my math. 2.3 times 1 divided by 352.441 times 25 divided by 1 times 22.4 should have given us 3.65451238 liters of carbon dioxide. Just like the previous problem, though, this is way too many numbers. It's way too detailed. We can only be as detailed as our initial measurement. So since I only have 2 significant figures here, I only need the first 2. So I need to look at my third number. Is it 5 or above? Then that means I need to round it up. If it's 4 or below, I just let it go, right? It's 5. So that means I need to round it up. So my final answer should be 3.7 liters of carbon dioxide gas. So now you think about it, it's like 3.7 liters. That's pretty big, because when I buy soda, that's at least 1 point something liters, right? So that means that if I have 2 of those big soda, from that 2.3 grams of wax that we burn, you release 2 bottles of carbon dioxide gas into our atmosphere. Okay, so that's adding up now. So now let's look at water, which is the other greenhouse gas that we release. So now let's look for mass of that water molecule or that water vapor that's released. So same exact thing, right? We're starting with 2.3 grams of C25H52. We're looking for mass of H2O. Pause the video now and go ahead and do your dimensional analysis. After a couple of seconds, I'll show you what I have. So this is what you should have gotten, your dimensional analysis. Again, our first conversion factor should be the same for all the problems that we're doing here, because we just need to convert that mass into mole. So again, 352.441 grams of C25H52. We need that to convert that into moles. Then now I'm looking at the water molecule. I know that I have a 1 to 26 ratio. So 1 mole of C25H52 and 26 moles of H2O, because now we're looking for water, right? So we do this, this grams cancels out, this mole cancels out. I'm left now, right now, with moles of H2O. I don't want moles of H2O, I want mass of H2O. So I need to do one last conversion factor of finding the molar mass of water. So the molar mass of water is 18.015 grams. How did I get that? Per oxygen is 15.999 grams. Each hydrogen atom is 1.008. So you add that together, you get 18.015, since I have 2 hydrogen atoms and 1 oxygen. So now this mole of H2O cancels that out. I'm left with the unit that I do want, which is grams of H2O. I need to do my math since I'm left with the unit that I do want in the final answer. So 2.3 times 1 divided by 352.441 times 26 divided by 1 times 18.015. Your answer should have been 3.056673316 grams. Like what we always do, significant figure. I'm only starting with 2 significant figures. My answer has way too many numbers. It's way too detailed. I can only be as detailed as my initial measurement. So my final answer should be 3.1 grams of H2O. So not that much. 3.2 grams, like that's not very much. So let's convert that into volume, how much space it's taking up. So now we want to convert that grams of C25H52 into liters of H2O. Follow your steps, right? Do your dimensional analysis. Go ahead and pause the video. After a couple of seconds, I will show you what I did. Now that you spent some time here converting that grams of C25H52 to liters of H2O or volume of H2O, this is what your dimensional analysis should have looked like. Again, first one should have been exactly the same, converting that mass into mole. Our mole ratio should be exactly the same as our previous, which is 1:26 ratio. The only difference is we're now multiplying that mole into 22.4 liters because we want to convert it into volume. Grams cancels out, moles cancels out. This mole of H2O cancels out that mole of H2O. We're left with the unit that we do want, which is liters of H2O. When you plug that into your calculator, you should have gotten 3.800692882 liters of H2O. That's way too many numbers. Again, significant figure. We only have 2, so we only need the first 2. So your final answer should have been 3.8 liters of H2O. Hopefully that gives you a better idea of how we're affecting our environment. Very little amount of candle burnt actually produce that many volume of the greenhouse gases that are released into the atmosphere. But let's put that into more practical concept, because like candles, who burns candles nowadays, right? So let's look at it from a practical perspective. I have a STI, right? And my STI takes up about 14 gallons of gasoline. Gasoline combusts and releases, again, carbon dioxide and water vapor. So when you drive your car, right, it releases pollutants into the air. Let's figure this out. My car, again, like what I said, contains gasoline that has octane. So when you look at your gasoline, the 89, 90, 91, that's the octane value of that gasoline that you're putting into the car. So the higher the number, the more octane it is, right? So octane formula is C8H18, right? When it combusts in your engine, it releases carbon dioxide and water. If my car uses up about 14 gallons of gasoline per week, and we know that 1 gallon is equal to about 3.78541 liters, how much in mass and volume of carbon dioxide and water vapor does my car actually release into the atmosphere? Heads up, it's not good. My car is actually very bad. So here you go. Go ahead and solve this problem. Again, follow your steps. Start with writing down the correct formula and chemical equation for your skeleton equation. After that, balance it, right? Then use dimensional analysis to solve the problem. And then after that, make sure that you look at your final answer and ask yourself, does it make sense? So go ahead and pause the video, write down your skeleton equation and then your balance equation. And after that, I'll show you how I figured out the correct amount of carbon dioxide and water that my car actually releases into the atmosphere. Okie dokie. So you should have spent some time trying to solve this problem. So let me show you how I did it. I'm going to start with how I balanced the chemical equation first. So again, I know I've been skipping this, but you always want to figure out write down all the elements that's involved in your reactant and your product. Write down how many you have of that specific element in your reactant and in your product. So if I'm looking at this, I'm starting with carbon. I have 8 carbon atoms in my reactant, only have 1 carbon atom in my product. So I'm going to put 8 in my reactant, 1 in my product. Then hydrogen, I have 18 total. So I'm going to put 18 in my reactant. I have 2 in my product. So I'm going to put 2 here. Then my oxygen, I have 2 in my reactant. So 2 here. Then I have total oxygen in my product, 3. Right now, I know that they're not balanced because 8, 1, 18, 2, 2, 3, not good, not the same. So again, law of conservation of mass states that whatever you start with should be the same amount that you end up with. So I know that this is not balanced. After you balance it, right, this is what it should have looked like. You should have gotten 2 moles of C8H18 combining with 25 moles of oxygen, which produces 16 moles of CO2 and 18 moles of H2O. So your balance equation. Now, again, if you look at the amount on my reactant and the amount on the product, they're exactly the same amount now. So now we're following the law of conservation of mass. We have the correct recipe to follow. So that should give us the correct amount of product that we're looking for, because again, our recipe is correct. The first thing that I did first to just get it out of the way is convert gallons into liters, because our standard volume unit is liters, not gallons. So I needed to convert that into the standard that we use into the equation. So 14 gallons of C8H18, right? The conversion that they gave us is per 1 gallon is 3.78541. So since I'm starting with the gallon unit, I want the gallon unit on my denominator because I want to cancel it out. And I want liters on top because that's the unit that I do want. So gallons of C8H18 cancels out. Now I'm left with liters of C8H18. When I do the math, I know that 14 gallons, right, is the same exact thing as 53.00 liters of C8H18. Why did I need to put this as 0.00? Because I have 4 significant figures here. My final answer should also have 4 significant figures. Now that I have my starting volume, I should be able to look at my stoichiometry map and use my dimensional analysis skill to convert that liters of octane into mass of carbon dioxide, volume of carbon dioxide, mass of water, and then volume of water, right? So I'm going to start with mass of carbon dioxide. I have 53.00 liters of octane. Again, I need to multiply that to 1 mole of octane to 22.4 liters of octane. Why did I do that? Because I need to convert that volume into moles. So when I do that, this volume cancels out that volume. I'm now left with the moles of C8H18, but I don't want moles of octane. I want moles of CO2. So I need to do the mole ratio of C8H18 to CO2. So this cancels out that moles of C8H18. I have now moles of CO2. I don't want moles of CO2. I want mass of CO2. So I need to put one more conversion factor of 43.998 grams of CO2, which is the molar mass of CO2 by looking at the periodic table, because you have 12.001 grams per 1 carbon. Then each oxygen is 15.999 times 2. That gives you 31.998. So combined, it's 43.999. Now that cancels my moles of CO2. I'm now left with grams of CO2. When I do my math, 53 times 1 divided by 22.4 times 16 divided by 1 times 43, that should have given you 1,665.676429 grams of carbon dioxide, but significant figure. So that means our final answer should be 1,666 grams of carbon dioxide. So that's a lot in mass. So now let's find the volume. Volume, same exact thing, right? So cancels out that liter of C8H18 by doing that first conversion factor. Now your mole of C8H18 cancels out this mole of C8H18. This moles of CO2, since we want volume, cancels that mole. Now I just need to do my math. 53 times 1 divided by 22.4 times 16 divided by 1 times 22.4 divided by 1 should give us our final answer. Again, math, if your numerator number and your denominator number is exactly the same, that's just equaling to 1. So technically all I did is 53.00 times 16. Our final answer should be about 848.0 liters. So if this is happening at standard temperature and pressure, I would have been releasing 848.0 liters of carbon dioxide into the air. Again, that's a lot, right? So now let's look at water. 53.00 liters of octane, convert that into moles, then multiply that to the mole ratio of octane to water, then multiply that to the molar mass of water. This is the procedure that I did. When you do the math, you should have gotten 767.2459821 grams, or using the right amount significant figure, 767.2 grams of water. So that's a lot, right? Now let's look for the volume of water that's being produced. Liters of octane to moles of octane, mole ratio of octane to mole of H2O, then multiply that to 22.4 liters, which is the molar volume. When you do your math, you should have gotten 954.0 liters of H2O. Again, if that was happening at standard temperature and pressure, I would have been releasing that many volume of both carbon dioxide and water. So since both are greenhouse gases, my car is actually not doing so well here. So again, if this is happening at standard temperature and pressure, 954 liters of water and 848 liters of carbon dioxide, that's a lot. But some of you guys might not care. Like, I don't drive, like, you know, I take public transportation, like I do a lot of the green things. Fine, sure. So let's do another example. What if you're camping? And to camp, you need to, you know, build fires or cook something, right? So let's do this another scenario. I love outdoors and I love camping. Let's try to figure out this time how much greenhouse gas I actually release into the atmosphere by burning my propane gas, which I use to cook when I go camping. Let's look at this problem. It says some camping stoves uses propane gas, right, which is C3H8 to burn. When it combusts, it produces carbon dioxide and water, which we know are greenhouse gases. If my stove uses up about 7.200 gallons of propane per day, or about 3.7851 liters per 1 gallon, how much in mass and volume of carbon dioxide and water does my stove release into the atmosphere every day that I use it? So per day, how many volume and mass of carbon dioxide and water do I release? Follow these steps. Pause the video. After a couple of seconds, I will give you the answers. Please double check your answers to see if you've gotten them correct. So pause the video now, and then after a couple of seconds, I will show you the answer. You should have started by converting your gallons into liters, because we can't use gallons in our conversion factor because the standard unit that we've been using is liters. So the first thing that you should have done is convert 7.200 gallons of propane into liters of propane. When you do that, you know that you get 27.25 liters of propane in that 7.20 gallons of propane. Now that we have that, we should be able to balance your chemical equation and then do your stoichiometry problem, or dimensional analysis. Your balance equation should be 1 mole of propane combining with 5 moles of oxygen gas, producing 3 moles of carbon dioxide gas and 4 moles of water. The mass from 27.25 liters, it should have been 160.6 grams of carbon dioxide. When you burn 27.25 liters of propane, you get about 160.6 grams of carbon dioxide. Now let's look for the volume of carbon dioxide. So this is the dimensional analysis procedure that you should have followed. The final answer here should have been 81.75 liters of carbon dioxide. All right, if you did not get that, please double check your work. Now I'm going to move on to water. The mass of water that you should have gotten is 87.66 grams. If you did not get that, please double check your work. And then the volume of water is 109.0 liters of water. From that 27.25 liters of propane, I used up about 109 liters of H2O. That's what it's equivalent to. Hopefully, you've learned a little bit more about dimensional analysis using stoichiometry. Hopefully, that made a lot more sense to you. If you have any questions, please don't hesitate to leave a comment, and I'll try to respond to you as soon as I can. Thank you again for watching this video. Hopefully, you've grown in wisdom and knowledge as you've watched this. Hopefully, now your stoichiometry problems will be a lot easier to do. Thank you for watching. Enjoy. See you when I see you.